So we're changing gears. We're talking now about like software engineering as a process a little bit, and specifically in Haskell, it is kind of really painful to do debugging, which you might be familiar with from other programming languages, where you can just sprinkle prints everywhere you want and kind of investigate what's going on. So in Haskell, it is sort of a little bit difficult. So let's have a quick kind of discussion or monologue on my side. What we are doing with software. So first question is, what is benchmarking? What is benchmarking? So think, if you have to do benchmark, what does that mean? What is it? There is a benchmarking framework built into Golang. So you can do unit testing and you can write benchmarks and run benchmarks on your Golang code. It's built into the language. It's built into the standard library and into the like standard toolchain. But what is it? Yep, those are quite okay. So benchmarking is measurement of performance. We're not optimizing anything. We're not debugging it. We're just measuring how long certain things take or how much memory some things use. So we're measuring performance. Usually it is in terms of speed, in terms of CPU and time. It could be over the usage of memory sometimes, but usually it is about time. And the main motivation is to observe differences. So if you have a CI/CD pipeline and you're benchmarking your software and suddenly someone did some changes and your benchmarks are much faster or much slower, then you say, oh, whoa, what happened? Like, why we are so slow now? So you can kind of go back and check what happened, right? So we're doing benchmarking to kind of keep tabs on what our software is doing. So we're identifying changes. We're not necessarily identifying performance bottlenecks. This one is actually, strictly speaking, not correct. This one is correct, to compare different implementations and to track performance, but to identify performance bottlenecks after changes. Yes, but not in general, right? So this one, what's profiling? Nope. We're not finding bugs when we're doing profiling. What are we doing? Not quite. So benchmark is, you're basically measuring how long things take. And you're taking a note of that. And you're saying, okay, is it running faster than yesterday or not? That's what benchmarking is, right? So benchmarking is checking how fast certain things work. Profiling is digging for the reasons. It's like actually finding out why something takes long time or why something is slow or why something uses a lot of memory. So you're answering question why. So you're digging for reasons and not just measuring. You're digging for reasons and you're doing measuring on the process, but the measurements are not that important. The outcome of profiling are the reasons. You are coming up with the flame charts or with the identifying the bottlenecks or identifying the critical sections or the functions that are used a lot inside the loop and so on. You're kind of answering qualitatively about why some things take a lot of RAM or a lot of time. You don't necessarily need to give a number, like how long it is. That's benchmarking. Benchmarking gives you numbers. Profiling gives you reasons, right? So we have those two processes. And then the final one is debugging. And this one has bug in the name, right? It is kind of, it suggests it's something about bugs. So debugging has to be something about bugs. So the name kind of suggests that we are kind of trying to find bugs, but we normally use debugging for a different reason. Why you do debugging often? Primarily, why people do debugging? Yeah, so finding problems, yes, and finding bugs, that's the legitimate use for debugging. You have a bug and you need to find it. But what else do we use debugging for, which is kind of not about bugs often? We often use debugging printouts or some form of variable checking, exactly to see how the code flows, to kind of understand what the code is doing. So we're doing it for ourselves. So we're basically tracking the progression of the program by doing debugging to sort of understand what the program is doing. And that's like 90% of the time, like or 95. We're not doing debugging because we have bugs. We're just doing debugging because we don't quite understand what's going on in our code, right? So that's why we do debugging. So we primarily doing it for understanding the code and for ensuring that the code is doing what we want the code to do, right? And then finding bugs, but that should be the primary goal. Like primary goal of debugging should be finding bugs. It should not be the other two things. A lot of people kind of disagree, but some people agree. And some people say that understanding the code should be done in sort of in a different way. So when you're a beginner and if you are starting to learn C or C++ and you kind of have a lot of concepts which are new to you, debugging is a very good learning tool. It's a very useful tool to use to learn how things work. But later you should sort of let it be only used for finding bugs. So understanding code, what can you do to understand the code? You can do mental walkthrough. You can kind of debug the code in your head. You can stare at it and sort of see how the variables change and how the code operates and sort of learn by staring at the code. It feels counterproductive initially, and it feels like it's easier just to sprinkle the code with printfs and just see them. But this is a skill. This mental walkthrough is a skill that you don't have when you start, and you acquire it as you train it, right? So the more you do it, the more you become better at it, and then you look at the code and you can kind of spot what is wrong by just doing it in your head. And if you imagine you're kind of doing code reviews and now we're working with AI and like AI gives you code and now you have to take it, put print lines in this code and to kind of do this, you would kill yourself, right? So like this ability of doing a mental walkthrough is something that you should kind of do. You should try to spend time and like understand what your code is doing just by staring at the code and doing the processing like in your head, like walkthrough in your head. It's super hard, like especially if you're not training it, it is super hard. So that's why we do other things. We use GHCI, we use this GHCI to tell us like, okay, how things work, like show me. And you interactively interact with it, you get help, you get like type definitions and things like that, then you sort of understand how things work. You can use AI for that as well. You can interact with AI to explain to you or to kind of guide you through some of the nuance. And then you have doc tests and unit tests. And this is a fantastic mechanism to understand what your code is doing, right? If you're writing a function and you want the function to behave certain way, then you write tests to ensure that the function actually does what it's supposed to do. And then when you implemented the function and the test pass, you have very good assurance that it's doing what it's supposed to do. If the tests fail, you will understand why the function is wrong by the test that failed. Like maybe some boundary conditions you missed. Maybe you didn't thought about of something. And then the tests give you the information. The tests give you the help for the mental walkthrough to find what the problems are. So doing the tests, using the GHCI and doing mental walkthroughs are the primary mechanisms for you to understand what's going on with the code. Doing print lines and doing kind of debugging, it's a bit of a crutch. It is good for finding bugs. If your code actually misbehaves, all the tests pass, and you kind of are stuck, like all your tests pass, but the code still does not work, like something is still wrong, then, you may need to do debugging. But most of the time you don't have to. And debugging is very time-consuming and a very expensive process, so you should try to avoid doing it. All right, so ensuring correctness, mental walkthroughs, GHCI, doc tests, and unit tests. So writing tests, like if something doesn't work, write a test to test it, and then the test will fail, and then write more tests, and then you will kind of get an idea of what might be happening. And the test will stay. Debugging is sort of one-off process, which doesn't leave you any value. Like the value which the debugging leaves you is in your head. And tests, like doing debugging through testing, like writing tests, leave the tests in. The tests are permanent. So there is added value to doing tests instead of debugging. So you kind of shifting the work to automation. You want the tests to be doing the work, not you. And doing manual labor, tracing the variables, like doing the printouts, then deleting them and so on, it's a manual labor. We should try to automate, and we should try to avoid it. All right, so what is it? What does it do? What it will print? Can you read the code and kind of try to see what F is at the end? Maybe it's too hard. Maybe you recognize the pattern. You see, like, it will take the first 5 values, right, of a list. Okay, we get that. That's easy. Like, that part is easy. So what is a list? A list is 0, 1. Okay, so we have already the first 2 ones. So it starts 0, 1. That's easy. And then we have this kind of a more complicated zip width, right? What's going on? Like if you've never seen Haskell before, you may be confused, right? But if you've seen Haskell before and you kind of work with zip and zip width, it knows that it zips 2 lists with a particular function. And then the first list is a list. So it starts with 0 and 1. And the second list is the tail of a list. So it starts with 1, right? So we kind of get the feel, yeah, okay, it sounds familiar. Maybe it is some sort of, sequence which adds consecutive numbers together, right? So you can kind of work it out. And like we're taking 5 and you already have the first 2. So what will be the next one? Like if we're zipping, the 0 is left out, and then the next is 1 and it is zipped with the tail. So we basically say, okay, so then it's like 1 and we binding it with plus. So it will be 2, right? So it's 0, 1, 2. And then we have the zip continue. So then we have 2 and we are using the 1 which was before it. So it will be 1. So we have 0, 1, 2, 3. And then we already have like how many? 1, 2, 3, 4. It's just 1 left. And you can work out the 5th one following the same logic. So you can kind of do it in your head, right? It requires a bit of effort, but you can kind of do it. All right, so what do you do with your code? So do you time your functions? Do you do benchmarking? Did you use benchmarking in your Golang, in your cloud course? Do you use the built-in benchmarking tools in Golang? Do you do profiling? Do you use external profiling tools? Do you use flame charts? So those three questions are all about profiling. Um, If you don't, that's okay. Most of the time we don't do it. Like doing the performance-oriented mechanics and like working on performance, it's kind of an extra skill. It's a separate thing. We usually build the software to do what it intends to do, and then we kind of fine-tune it for performance. But think about it and think about like, for example, in the cloud, you could do some benchmarking for your servers, for your REST APIs. You can identify like why it takes longer than you thought, or maybe what can you improve to handle more traffic, right? I mean, you may not care, like it's just a school assignment. So like if it handles 200 requests per second, who cares? Like I could do 2000, but maybe you care. Maybe you say, yeah, how many requests per second can I do, right? So then you can play with this. Okay, so profiling and benchmarking, try doing those things, try timing your stuff, try using the built-in tools, especially for the cloud with Golang. It is actually quite fun. So debugging. Do you do debugging in your IDEs? Do you do printout statements? Do you do command line debuggers? Do you look through variables in the IDE debuggers? Do you use those things? So it's fine. You should try to think what can you do to reduce the number of printouts that you are using and do other things such that over time you're doing less of those things. It's fine to do them. And as I said, it's a fantastic tool to learn how things work, but try to think when I don't have to use it anymore. Like try to force yourself not to do it. Like you are kind of tempted, like, oh yeah, I need this print line here. Maybe like resist and kind of try to walk through mentally or try something else or try to write a test. Like, okay, I don't know how exactly it works. Maybe I can write a test and I will kind of understand like how it behaves under those particular conditions and so on, right? So it's okay. It's not that you should never do it. You should do it, but you should try to over time do less and less of debugging. I mean, you have to find bugs. If you have bugs in your code, you have to find them. But if you're doing it to understand your code, then you should try to reduce it. So avoid manual debugging, basically, is my message. So what to do instead? For understanding, do mental walkthroughs and use GHCI, call your functions, like play with it, play with your code in an interactive way, and write tests. For correctness, do tests, right? For ensuring correctness, you do tests. So what if you have to find a bug? Well, write more tests. Maybe the test will reveal you where the bug is. Maybe you missed some edge conditions and stuff like that. And then do mental walkthroughs. Start with that. If that does not help you, if that leads you like you haven't found the bug, then you have to do debugging, right? So why debugging in Haskell is difficult? What are the reasons why debugging Haskell is difficult? Exactly. It does not allow side effects. It's like purity is the mantra. So Haskell is a purity-oriented language. It makes side effects hard. So debugging is hard because of that. Also, it's a lazy language. So a lot of things happen during the execution, depending on like when and how other things happen. And because of the laziness, you cannot force certain things to reveal what they are. It's declaration oriented instead of like execution oriented, right? So the flow of the execution is a little bit detached from the logic of how you declare things, right? So it's a little bit tricky because of laziness, because of the side effects, and because it's like functional, like you have those functions going everywhere and passed around, and it's kind of, you don't kind of have a lot of variables often. Sometimes you have no variables to trail. You just have results of one function being chained to other functions, and the flow of processing is like not nice for extracting the intermediate results because of laziness and because of this like functional intertwine. So it is hard. So it's lazy, declarative, and purely functional. So it's kind of, it makes debugging Haskell hard. And you hit that wall very like head on, right? You try to understand, you try to put the printouts out like into the code, and you can't. And it's like, oh, far out. What do I do now, right? So, well, if you really have to do debugging, then try to avoid it, right? I really encourage you not to do debugging in Haskell. But if you really, really, really have to do it, there is like a hack. There is a hack which is called trace. It's inside debug trace, and it is sort of like a print line statement which you can sprinkle into your code. It is a little bit kind of fun to work with because the trace function is quite interesting. It basically takes a string and a value, and it returns a value. So you can kind of inject it anywhere where there is some sort of result or where there is some sort of value, and kind of put that string in, which will be printed when that value is kind of, when the code hits that trace call, right? So everywhere where you have some sort of value, you can wrap it around into the trace, and it will work as if you have a print line statement there, right? So it is a very cheeky way of kind of introducing printouts in your Haskell code. So here we kind of have the declaration. So we're using trace. The function takes a string and a value and returns the value. So it is kind of doing nothing. It just takes something and returns it. But you have this extra parameter, which is the extra string that you can use, right? And then you have extra methods that you can use, which is trace show and trace show ID. They are kind of similar. They just don't have the string. So I usually, if I have to, I use this one, but you can use those as well. Those are more generic. So the first value in this case is a string, but here you can kind of inject what you want to get. All right, so then there is some kind of a recursive call. We're doing some things, and then we kind of doing the step and so on. And then you can see the normal call would just have accumulator plus plus and accumulator plus plus for this branch and for this branch. But we say, okay, we want to see what's going on. So we can inject, we can wrap around this accumulate plus one inside this trace and have something printed for us. So we are kind of printing what is n, we can print what is ACC, we can print whatever we want, right? And then you can kind of walk with this. All right, kind of a question, final question of the quiz, if you're paying attention. So if you see this in the code, what it will produce? Yes, it produces 42, the second argument, and at the same time, it will print the message to the console. It will bypass all this purity and everything, and it will just dump something on the screen, right? All right, so that's it. I hope I discourage you to do debugging, but you can give it a try and you can see if it is useful or not. Most of the time, it actually is more confusing than doing mental walkthrough. And it also takes some gymnastics into using it because you need to know where to kind of inject it. For certain faults or certain things, yeah, I feel it's kind of easier to actually understand how things work, like with the mental walkthrough, but give it a try. So this is it. I ask you to watch a video about the C++ regime. And in that C++ video, who watched the video? You watched it? Okay, I encourage all the others as well. She's quite fun, like talking about jet software and developing C++ for military. To encourage you to watch this video, there will be one exam questions, which is a fact from that video. And the question is, how many programming languages have been used in US defense at one point of time? If you watch the video, you will know the answer. And if you didn't, you will have no idea. So watch the video, right? That's the exam question, which I will put in. How many different programming languages were used in US military or defense department at one point of time? All right, so she talked about three things. Cyclomatic complexity, we talked about it last time. So you sort of know what it is and why we should control how complex our code is. She talked about not allocating memory, which is kind of nice. We don't care, like with languages that we're currently using, like Golang and Haskell, we sort of like, okay, memory, like it happens for us, like we don't kind of care too much. When we go to Rust, we will care. We will have to do manual memory management, so you will be a little bit more on the page with the memory thing. And then she talked about panics, and she said no exceptions allowed, no panics, like everything needs to be handled, no blue screen of death. Nothing kind of can happen in such a way that the program crashes, right? If you are in a fighter jet and your software crashes, then people will die, right? So those things were really interesting and the same as we discussed last time. But she talked about one extra thing, which was not using recursion, right? So she said recursion is forbidden because we can have a stack overflow. We can kind of call recursively too many times, and we have a stack overflow. This is partially true, but it's not completely true. So in C++, most of the time, if you are doing recursive calls, it's a bad thing, and you should avoid it. In some languages, like Haskell, we're using recursion a lot, right? Like we would not live in Haskell without recursion because we would not be able to do loops and we would not be able to do much. So we have to use recursion. So is it bad? Not actually. It depends. So in lab 12, there are two things. So for today, you have two things. Let me go to lab 12. Task 12. So there are two things, and one is called recursion, and it kind of talks about two types of recursion. One, which is a normal recursion, which is bad in a sense that it potentially can overflow the stack. And that one for critical applications should be avoided. But it also talks about tail recursion. And tail recursion is the trick that we often do in Haskell that does not have that effect, that actually is exactly the same as doing a loop. And the compiler can optimize the code in such a way that it uses like goto statement instead of putting the next call onto the stack frame and kind of doing the stack allocations. So with tail recursion, most compilers in most programming languages are able to optimize the code in such a way that there is no usage of the stack at all. It's just one frame and it is basically a loop, even though the code is recursive. the code calls itself, the function calls itself, right? So this exercise kind of talks about this tail recursion, and it will be on the exam as well. The exam, there are like 2 questions about tail recursive functions. So you need to be able to recognize which functions are tail recursive and which ones are not. Which ones will use the stack and which one will be fine not using the stack at all. A fun fact, JVM, Java, when it came about, when the designers developed the JVM, they were, you might say, a little bit lame. They didn't thought it through. So JVM on the bytecode level does not have ability to optimize tail recursive calls. So in Java, most of the time when you're doing recursion, it's a bad thing. You should avoid recursion because it cannot be optimized to be like a loop. But in .NET, the designers of the virtual machine and the bytecode were a little bit smarter, and they knew about tail recursive recursion. So they've built that in. So in .NET, if you're doing tail recursive calls, it's perfectly fine. It will be as optimal and as fast as loops. So even though I personally am not a big fan of Microsoft, and I feel they are sort of one of the evil kind of companies, I have to admit that the .NET VM is superior to Java VM because of some of the engineering that went into designing it. It's the same with WebAssembly. WebAssembly knows about tail recursion. It is built in because JavaScript often uses it. You have a lot of recursive calls in JavaScript, so it has to work with it quite well. So recognize when tail recursive calls are happening and when it is fine. And recognize which ones are not tail recursive and they cannot be optimized and they will use the stack, right? So the first exercise is about recursion. I have a question. Yeah, so Scala is doing a trick, and they're doing a certain unrolling of the code before it hits the compiler, the bytecode compiler. So they kind of doing a little bit of static code analysis, and they sort of doing it a little bit outside of the kind of language itself. So I would have to check it, but I suspect it sort of happens before things hit the Java compiler itself. Yeah, that's a good point. I will check how Scala does it, because Scala is like a functional language on top of JVM. Similar with Kotlin, like Kotlin probably is doing something similar. So yeah, thanks. I will check it out. And then the second thing is a calculator. The calculator is a simple exercise related to execution of expressions that you want to evaluate. And it again guides you through the reverse Polish notation and how to interpret as kind of expressions and evaluate them with the use of stack. And it has 3 implementations. The first one is a very naive way of dealing with it in Haskell, with passing everything through calls. The second one uses applicative, and the final one uses a monad. The first one you all should be able to do. Like it is like a very basic Haskell. There is no magic in there, and it's relatively simple. It's just functions and parameters to functions. So it should be pretty straightforward. The second one with applicatives, you should also be able to do quite easily with what you already know, because it is just using the maybes and eithers, and it's sort of the familiar territory, okay? The third one, though, is using a state T, which is a monad for carrying state, and it kind of demonstrates how can you carry state for your execution in a very nice and compact way. This one is a bit advanced. So if you feel it's over your head, that's fine. Like you don't have to do the monads, you don't have to do state T. But if you feel, oh yeah, that feels kind of nice, and I can like see how it can be used in my programs, then I encourage you to kind of try it out, to sort of learn a little bit more about monad transformers and how to deal with state in Haskell. It is a little bit of a steep learning curve. It is a material which goes a little bit beyond like the foundations. So you may decide, no, it's too much, I'm not doing it. But if you want to get like, you know, B or A, you should dive into it. You should kind of try to understand how carrying state using these monadic transformers work and like what it gives you. So it builds up gradually. It builds from a very simple one to this kind of intermediate with applicatives. And then it kind of goes into the transformers. And that's the most nice, the you know, the most beautiful or the most robust and the most desirable implementation is the last one, okay? So the lab is going through some, it is like a self-running, like you just read through and kind of follow the instructions and try things out and kind of try to learn. I set the deadline to be next week because I think there is a little bit of thinking you have to do and it takes a little bit of time. So it is not something like the first part you can do in the class and that would be fine. But the applicative and the monad parts are a little bit more material that you need a little bit more time to work with, right? So try to dig into this and try to do it. I set it to 11th, so just 1 week, but if you feel you need 2 weeks for it, I'm fine. Like there is no really time pressure or anything, so I can extend, to 18th if you feel it's better. So who feels it should be 11? So you all feel it should be 18th. All right. So let's make it until 18th. All right. So any questions? So the tail recursion is an important topic. Go through the exercises, try it out, try to find which functions are tail recursive, which are not, and try to get this pattern of the helper function kind of in your head. Like, how can I make my recursive call tail recursive such that I still have recursion, but it does not use stack, okay? Usually that means you have a helper function. And then do this expression thing. We have a bigger project coming up. So after this lab, we have a lab which relates to languages and to doing a little bit more with languages, not just the expressions. And then we will talk a little bit about Rust and we will talk a little bit about WebAssembly. So that then the next, let's say, 2 topics are a little bit more heavy than what we had so far. So paying attention to this calculator exercise will really equip you to deal with this more complexity in a very easy way. If you don't do it, then you will struggle because the next things are a little bit more heavy, right? So I encourage you to do the calculator lab. Okay, so the final thing is I don't have it as a material, but for those of you who are really on the geeky side and are really onto the learning about recursion, there is this concept which is called Y Combinator. And do you know, have you heard about Y Combinator? So, okay, so it's called Y, capital Y Combinator. So combinators are usually functions which take other functions and they do something with them. That's the like we call operator, which is something which takes 2 values and produces a value, and combinator is something that takes functions and produces a function which does something else. And Y Combinator is a big, if you say Y Combinator, it's a big venture capital software company which funds software companies in Silicon Valley. It's like the funding startups and funding students and so on. So it is sort of a very famous and very big, one of the biggest IT or tech venture capital companies. And it's called Y Combinator. So why the name? Where is the name coming from? The name comes from a Haskell query. Haskell, okay, rings the bell. It's a guy by why we suffered the Haskell, and carry about carrying functions, right? That's also because he was called, his surname is Carry. And then there is this kind of a combinator which turns an ordinary function into a recursive function. It's a little bit of like mental gymnastics. So if you're really on the geeky side and if you really want to go dive into this rabbit hole, you can kind of go a little bit and read about this, okay? I don't have slides, and I spent like 2 hours preparing a lecture about this. And then I said, no, Mariusz, we're not doing lecture about it because the students will hate you. But those of you who wants to go into this rabbit hole, you can go. And I'm sure you will learn a ton and you will really enjoy it, but you have to kind of want to do it. I don't want to force you. It will not be in the exam, but it's a really fun thing. And when I was a student, I was not forced to do this neither, but our teacher mentioned it, and I kind of went into the rabbit hole for like, you know, a year. And it was kind of it was an interesting journey. So you can read about it. You can read about different combinators. You can read about Y combinator, and there is a kind of a Z combinator as well, which I had for the lecture. As I said, I spent literally 2 hours preparing the lecture. I even have like some Golang code to go with this lecture. And then I said, no, like I'm not doing it. So, and for Golang, we have to use Z combinator because it is not a lazy language. In Haskell, we can do like a proper Y combinator because it is a lazy language. But anyway, if you want, you can go. And the keyword here is like how to turn a non-recursive function into a recursive function. So it is like a little bit of really mental gymnastics. So go there if you want to. Skip it if you don't feel it is your, you know, yeah, your bread and butter. So, all right, so that's it. Any questions for those two? If not, then please have a look. Start with the recursion because the recursion is sort of a more of a lecture style, like it explains kind of a concepts, and then go into the calculator. Everything is described in the README file. I will now change the deadline to be 1 week later. All right, thanks.